Welcome to This Explainer. Today we're diving straight into the absolute bleeding edge of cosmology. We're going to bridge the gap between those mind-bending chalkboard equations of theoretical physics and the incredibly advanced observational missions exploring the deep vacuum of space right now. If you've ever looked up at the night sky and felt a sudden wave of awe and curiosity, you're in exactly the right place. Let's get right into it.
So let's kick things off with a real brain teaser, famously raised by the team at PBS Spacetime. How on earth can an infinite universe have a boundary? It sounds like a total contradiction, right? I mean, we're always told the universe has no edge, yet astronomers constantly talk about the edge of the universe. To unpack this, we really have to reframe how we think about scale, time, and the physical limits of human perception.
And we're going to answer that grand question by moving through 5 cosmic chapters: the edges of our universe, mapping the dark cosmos, hunting for alien worlds, observing active black holes, and finally, the fate of the universe.
All right, Chapter 1, The Edges of Our Universe, Theoretical Boundaries.
This is basically a giant cosmic feedback loop that drives modern cosmology. On one side, you've got theoretical physics. Places like the Perimeter Institute and all that dense, cutting-edge research hitting the archive physics and cosmology platforms. They're the ones asking the profound questions about space-time. Then, on the other side, you have observational astronomy, global heavyweights like NASA and ESA actually building the multi-billion-dollar metal machines to gather the hard data. It's this continuous, beautiful loop of human imagination and hardcore engineering.
So let's think about our physical limits for a second. Because the speed of light is finite, and the universe has only existed for a finite amount of time, right around 13.8 billion years, there is a strict mathematical limit to how far out we can see. We call this the particle horizon. Beyond this horizon exist thousands or maybe even infinitely more regions of space that we simply can't see yet, purely because their light hasn't had enough time to travel across the cosmos to hit our telescopes.
PBS Spacetime really hits the nail on the head here. They describe our observable universe as a tiny patch of land in a vast plain, and this boundary is like building a little picket fence around it. The crucial takeaway? This picket fence is not a literal brick wall at the end of space. It's just the limit of our perspective. Drawing this boundary just makes our crushingly insignificant little patch of the cosmos feel, well, a bit more homey. It's not the edge of the universe. It's literally just the edge of our vision.
So, with our theoretical boundaries set, how are we practically looking out into all that dark? If you've been reading Cosmos magazine lately, you might be wondering, what are the tools actually making headlines for stretching our horizon as far as mathematically possible? Which brings us to Chapter 2, Mapping the Dark Cosmos, Tools of the Trade. These are our current cosmic search engines, the exact missions you'll constantly see highlighted on the NASA Universe and ESA Cosmology portals. We've got ESA's Euclid telescope mapping galactic structures, NASA's TESS hunting down exoplanets, and the SWIFT observatory watching for extremely violent black hole activity.
It's honestly incredible to see how these global agencies tag-team the biggest mysteries out there. Right now, ESA's Euclid is actively piercing through the incredibly crowded, dust-choked heart of our very own Milky Way. And the data it's gathering is essentially laying the groundwork for the core survey planned for NASA's upcoming Roman Space Telescope. By collaborating like this, they're mapping out millions of stars and helping us decode the dark matter that physically holds our entire galaxy together.
But you know, when we have all these incredible telescopes mapping millions of stars, and we know there are just countless planets out there, we inevitably crash right into the famous Fermi paradox. With all this prime real estate in the galaxy, why haven't we heard from anyone else? Seriously, where is everybody?
Let's dig into that in Chapter 3, Hunting for Alien Worlds, the Search for Life. Columbia University's Cool Worlds Lab ran this massive poll on why we haven't found any technological civilizations, or what astronomers call technosignatures yet, and these were the top hypotheses. The zoo hypothesis suggests advanced aliens are basically just watching us from a distance, treating Earth like a protected wildlife sanctuary. Then there's the dark forest theory, which is definitely a bit more terrifying. It suggests civilizations are deliberately staying dead quiet to avoid being wiped out by hostile predators. And finally, the grabby aliens hypothesis, which argues that aggressively expanding civilizations do exist, but because the universe is just so incredibly huge, they simply haven't reached our specific neighborhood yet.
But hey, there's a fantastic silver lining here. Even if we haven't bumped into any aliens just yet, our search is yielding some truly wild physical discoveries. Take NASA's TESS mission. It recently located the literally puffiest planets ever found. We're talking bizarre, incredibly low-density exoplanets that completely challenge our previous models of how planets even form. It seems like every single time we look for life, we just end up discovering how delightfully weird the physics of our universe actually is.
All right, pivoting away from those peaceful, puffy planets, we have to confront the other extreme. What happens when the forces of gravity become so overwhelmingly powerful that they literally rip stars to pieces?
That takes us to Chapter 4, Observing Active Black Holes, Extremes of the Cosmos. Imagine a star wandering just a bit too close to a supermassive black hole. What happens is a tidal disruption event. The gravity pulling on the near side of the star is so much stronger than the gravity on the far side that it literally stretches the entire star into a stream of superheated gas. This intense gravitational shredding, which physicists playfully call spaghettification, creates a massive, blinding flash of X-ray light. And that single flash of light is exactly what allows our telescopes to spot the black hole in the first place, because otherwise it's completely invisible.
And here is the craziest part. We are actively watching this happen. In a super rare event, NASA's Swift Observatory recently spotted what they're calling a snacking black hole. Instead of just devouring the star all at once, this black hole is slowly stripping a sun-like star every single time it loops past in its orbit. The star actually survived the initial encounter and just keeps coming back for more, which is giving scientists this incredible, highly predictable glimpse into a star's terrifying death spiral.
This whole situation perfectly captures the sheer grit of observational astronomy. The Swift Observatory was launched back in 2004 for what was supposed to be a quick 2-year mission. It ended up lasting 2 decades before a gyroscope failed in 2024. But scientists absolutely refused to let it die. In a landmark move, NASA contracted Catalyst Space to launch a robotic mission this very month, June 2026, to physically boost Swift's decaying orbit and extend its scientific life, all so it can keep hunting down these snacking black holes.
Now, zooming out from the heroic survival of one very resilient satellite, we eventually have to face the ultimate existential elephant in the room. With stars dying, black holes snacking, and the universe constantly expanding, where is all of this heading?
Which brings us to our final chapter, The Fate of the Universe, Existential Conclusions.
The phenomenal science communicators over at Kurzgesagt have thoroughly explored the actual math of cosmic endings, and theories propose a few fun ways the universe could be destroyed, like the Big Rip or heat death. Eventually, trillions of years from now, the very last stars in existence, these tiny, slow-burning red dwarfs, will just fade out. But rather than despairing at the eventual decay of everything into nothingness, we can adopt a philosophy of optimistic nihilism. Think about it. If the universe doesn't have some inherent eternal purpose, then we get to dictate our own purpose. We get to find profound joy and awe in our fleeting, highly improbable existence right here, right now.
I think this mindset is beautifully captured by the late Stephen Hawking when he was talking about the Perimeter Institute. Despite the staggering, crushing scale of the cosmos, the violently destructive physics of black holes, and the eventual, inevitable end of the universe itself, humanity's drive to decode it all remains our absolute greatest, most optimistic endeavor. We are literally a way for the cosmos to know itself, and we should be expecting great things to happen as long as we keep looking up.
From the theoretical edges of our particle horizon, all the way to the X-ray flashes of snacking black holes, this universe is vast, bizarre, and just waiting to be understood. And this explainer, we've barely scratched the surface. So what part of the mystery are you going to dive into today? See you next time.